Hi everyone, welcome to Seismic Data Processing course. So we'll continue our lecture. We have within the pre-processing, we have geometry, spreading correction, and trace balancing. We have something called spherical divergent compensation. So when the seismic wave expand within the Earth's surface, let's go from the source into the ground. The wavefront expand spherically, and the amplitude will be decrease with depth. So amplitude decay with depth, and also the amplitude decay with opposite. These called the amplitude decay or spherical divergence. So we use something called a spherical divergent compensation, this type of the gain correction, to restore the lost amplitude. So the goal to restore the true reflections amplitude so the deeper events are not artificially weak compared to the shallower ones. Geometry separating, so the amplitude decay due to the spherical divergence can be expressed as we have the homogeneous in case we have a constant velocity, but this is not our real case because in most of the time we have layered space. This velocity change with depth. So we use the gain function becomes we have the root mean square velocity divided by the initial velocity, and then two-way travel time. This is over the power 2, and then two-way travel time divided by the initial two-way travel time. Formula account for variation velocity with depth. We have the geometric separating. Seismic data shows amplitude decay due to wave separating. Large amplitude events can dominate the record because the low amplitude will be decayed because these lost energy will be absorbed by the material. Harder to identify weak reflection events, and also large amplitude contrast distort digital effect used in the processing. So the physical explanation here we have when the energy seismic wave would go through the ground will be lost the energy. The more deeper it go, the more energy will be used. And in case if you have the homogeneous, the constant velocity, the estimated amplitude reduce will be 1 divided by the velocity at a specific time, but when you go deeper, the estimated the amplitude loss will be divided 1 by the velocity square at a specific time. So the more deeper we go, the more amplitude will be very low. And this decay can be estimated using energy conservation principles. So we are applying some type of corrections to enhance this low frequencies. So we have the Q attenuation. When the seismic wave travels through inhomogeneous or anisotropic rocks, part of its energy is scattered and absorbed. This causes frequency dependent attenuation, meaning high frequencies lose energy faster than low one. The amplitude, the strength, and the phase timing of the seismic signals change as a result. So we have something called the quality factor. This is qualified how much energy loss occur. If we have a high Q value, that means less attenuation. That means energy travels farther with less loss. But if you have high Q, that means a strong attenuation. That means energy decays quickly. So we have the frequency and we have the distance. When the distance is increase, when the distance here is increase, the amplitude, the frequency will be decreased, and the amplitude also will be decreased. When the distance will be increased, and here we have the amplitude frequency will be decreased also, and the amplitude will be decreased. So the absorption and the transmission, other cause for amplitude decay. So the decay is happening because two factors, the absorption and transmission. The absorption when the seismic wave travel through the ground, so it will be absorbed by the rock materials. This is the medium, and we have the transmission loss, and when some of the wave are reflected or refracted, some of the energy will be lost. This is the wave conversion. So the decay depends on two factors, the time and the frequency. With time, if we have a longer distance, that means we have a longer time, and the longer time the wave is going to, the more frequency, the more amplitude we lost. The amplitude will be lost when the time is longer, that means the distance is longer. When going deep the amplitude will be lower and lower and lower. So in order to make it very clear, the low frequencies, we apply the gain corrections to enhance the low frequencies, so it will be so easy to see and understand. And these are the Q value depending on the rock type. So if you have this for clay and sand, sandstone, shale, and we have limestone, for each rocks we have different type of Q value. If you have different type of Q value, that means different type of velocity, and that means different type of decay. Have the gain as refers to the amplifying the strength amplitude. So with strength amplitude, if we have weak reflections, these weak reflections we can do some corrections to make it very clear. So we have two types. One is called automatic gain control. This is automatic normalize the amplitude of seismic data with a short time window rather than over the entire trace. The advantage of automatic gain control, it's equalize the traces. That means the high frequency and low frequency, it will take the average and divide it by the all. Improved stacking, it will sum all the traces and separate this gain over the low and high frequency. Enhanced deep reflections, that means the deep reflections, that means you have low frequency, it will enhance them. But we have the disadvantage also, no physical basic for amplification. So it's not representing the true subsurface geological layers. And we have shadow effect because the high frequencies and the low. They have the low frequencies. When you apply the corrections, these low frequencies will be hidden because the effect of the gain on the high frequency. Amplification of noise, that means when you apply the gain, you will add more noise to your data. So the gain function, we have the corrected amplitude, we have the initial amplitude, and then we have linear gain and exponential gain. And this is the symbol of how is the gain work. If we have this, the seismic signal, so within the low frequency we can enhance when we increase the gain. If we can decrease the gain, we'll enhance the low frequency. So we'll add more to enhance the low frequency. So it's easy to see and it's the changing with the signal. And this is how the AGC, the automatic gain control. First you set the average, you set the root mean square, the average amplitude, and then we set the maximum amplitude and then compute gain factor. So the gain factor will be the average amplitude divided by the maximum amplitude. And we're going from this input, the low frequencies in here, to enhance the low frequencies. We have time variant gain. This is also a type of gain function that increases with the time to compensate for energy loss. Seismic wave travels deeper. Also we have the equation. This is the initial amplitude dividing by time variant gain function. So we have the input, and when we apply the linear gain, we have the gain function. We have this is mt, m multiplied by the time plus c, and we have the m is the slope and the c is the interface. So we're going from this input into this output. And also we have exponential gain function. This is the time multiplied by the c, the interface, and we're going from this input to this input. So the optimization value of c, this is the we are looking to find. So we have the time variant gain, we have the near and we have the far, and the near depth and far depth. So in the near depth, if you have any corrections, you can go from this one to this one, and the far depth we're going from low frequencies to enhance the low frequencies. But we have another method called trace balancing. This certain application, such as the first break picking, require the maximum amplitude of all near to far offset traces to be balancing at a user-defined RMS sampling. So this one, trace balancing, is considered the vertical frequencies and also the horizontal, the opposite. And so set hues define desired the RMS amplitude, and then scan traces to get the maximum amplitude, and then we define the average amplitude divided by the maximum amplitude. So going from this input to the output. comparing between the TVG and the trace balancing. Within the TVG, you will have enhancing but a very little low. With combining the trace balancing that take the vertical and opposite, you will have better output. So the key point in here, if you have the geometrical separating, we use the gain to correct our low frequencies, so it will be so clean to see and understand. If you have attenuation convolution, so we use the deconvolution, we'll describe in the next video. And also if you have a noise, we use the band filter, the one that we practiced in the previous lectures. So this is all you need to know about these two processes. Thank you for watching and see you in the next video.